Okay, we're going to continue our lecture on field effect transistors. I believe the last thing we were talking about was a FET is normally with this gate to source junction reverse bias. Remember, an FET all FETs use a voltage to control a drain current, also a source current. We're currently looking at the junction field effect transistor, or the JFET. So remember from our lecture last night, a JFET actually has a p-n junction, but it is a unijunction, which means it's only got one junction in there. And of course, we look at the different arrangements that we can connect this thing in. And of course, similar to the BJTs, the BJTs, we can hook them common emitter, common collector, or common base. Well, in the FETs, we can hook them common source, common drain, and common base. Common gate, excuse me. So common source, common drain, and common gate. And of course, remember how we identify the leads. Go ahead and start the slide so I can draw on this. We identify the leads by looking at them, and this lead at the top, and this is the drain, and the lead down here at the bottom, this is the source, and this lead right here would be the gate. And of course, this is the symbol for an N channel JFET. Input resistance, we're not going to really look at in this class, even though these guys have extremely high input resistance. And we'll show y'all a common source circuit here in a second and show y'all basically how it's biased. And in fact, we'll switch over to that right now. And once again, this is from the school, logged into one of the computers at the school that's running an electronic workbench. So this is a common source amplifier. And you notice, let me get rid of a couple of these things. What you notice is that what's nice about the JFET, we've talked about an important concept called impedance matching. And the ideal amplifier, if we're going to amplify a signal, would have infinite input resistance or input impedance and have zero output impedance. So if the amplifier had zero input, maximum infinite input impedance, that means it would not load the signal at all. If it had zero output impedance, it means the amplifier could supply an infinite current. Unfortunately, neither one of these are we're not capable of getting either one of these in electronics. So they came up with a method that we refer to as impedance matching. Impedance matching is a process where if you match the impedance in a communication system, then you get maximum power transfer between the source and the load. So what we shoot for is impedance matching. It's extremely hard to get impedance matching on a bipolar transistor because there's so many variables on when the current comes into the base and it splits up and moves around. Well, what we can do with an FET is we don't have to bias it with a voltage divider. So what we've got right here is we've got a 1 megohm resistance, which would hopefully match it to the impedance of this generator right here. Okay. And what we got is, since there's no current flow through it, then legally this guy right here drops, the only voltage it drops is the power supply voltage. So when the power supply voltage comes screaming in, then it's its return path. But what it does is placing that reverse bias voltage over here also on the gate and controlling the gate voltage. So what happens, there's a lot to the design on an FET, just like there's a lot to the design on a bipolar transistor. But basically what we do is we choose the drain resistor and the source resistor. And when this thing comes on, what happens is we have a current flow through this 100 ohm source resistor. So this is the guy right here that is actually giving us the bias. So what happens when we have current flow through this, it drops a voltage, which makes this point right here positive. Well, this guy's setting at 0 volts. This guy is setting at a positive volts. So when we measure the voltage gate to source, what we find out is when we measure this voltage right here will turn up being negative, which is really, really neat. So what happens is when the current flows through here, it generates, makes this positive. If this is positive, this over here is negative in respect to this voltage, right? You understand? So when we say gate to source voltage, what we do is we'd put our common on the source, and then we would measure to the gate, and what we would measure is we would measure a negative voltage. So I'll pause the lecture just a second so I can move my meter around. So what I've done is I've came over here and I put my positive lead on the gate. So when we say gate to source, remember it's very similar to the measurements on a BJT. The one we say last would be the common. You know, so when I say base to emitter, then we would put our common on the emitter and then we would measure to the base. Well, here we're saying voltage gate to source. So notice I have the common of my meter here, and then I have my positive on my meter here, and it's measuring a minus 50 millivolts. Well, how did that minus get there? Well, when this current flows through the resistor, it drops a voltage, which means, and here's your positive up here, and remember when you measure, you set up the polarities on your resistors back in DC, is the side of the resistor that's closest to the positive, or vice versa, gets the positive sign. So this would be positive, negative in respect to the other side, and then this right here would be positive in respect to this. But what happens is, but this is common. So what we're going to say is, okay, if I put my negative here, and then I measure to my base, my gate, what we come up with is the gate actually sees a minus 51 millivolts, which starts driving the FET toward cutoff. Remember, in an FET or JFET, get those straight because we have different types of FETs, but on a JFET, you get maximum current flow through the channel when you have 0 volts on the gate. So what we do is we reverse bias that. So remember, this is P, this is N, this is an N channel. So when I put this in here, this becomes negative. So we're putting a negative on the P, and what does that do? Well, if I put a negative on the P, what it does is decrease the size of the channel, which causes the current to go down. And this is the way these things bias. So we call them self-biasing. So that means on a bipolar transistor, we have to bias it over here on the base. But on a JFET, we bias it usually over here on the source. And we use this resistor to set the input impedance of the amplifier, which is really neat. So these guys here are a little easier to design. Choosing this size resistor is critical. You have to look at the spec sheets and play around with it. But once you got it set up, then it's pretty easy to work with. So this would be what we call a common source amplifier. The common source amplifier, of course, has a high input impedance. It has a moderate output impedance. The input impedance, if we didn't have this guy right here, it would be infinite. And of course, we really, the higher the input impedance is, the more noisy the amplifier becomes also. So this gives us a way of setting an extremely high input impedance, but not making it infinity. So and notice it's pretty much well over on this side. The common source is very similar to the common emitter. The big difference is over here, we're not required to put that voltage divider in the circuit. So this is a common source, Now the other ways we can hook it, so this is in your textbook. I don't actually know what page this is, but I'll know it's in chapter chapter 11, they don't give us the page numbers. They draw them kind of strange because that this is not normally the way we would draw these things. You know, so if I was to come redraw them the way you would probably see them on a schematic, as soon as I get my drawer up here, the way we would probably draw it, the way you would see this on a schematic, is we'd have a power source up here at the top, of course, and that would be here. This would be our drain resistor, and it would come through to the FET or the JFET, and of course this is an N-channel JFET. Here's our source resistor, and then this would be our gate resistor. Now, of course, here they're just drawing the bias of the thing. So this is the way we would draw it. This is the way our schematic would look. And of course, this would be VDD. Now, this is VDD because this is the drain resistor. Generically, we refer to this as RD, and we refer to this as RS, and we refer to this as RG. Now, when you get out in the real circuits, these are going to be R1, R43s, R67s. It's just that we give these things a common name. Now, notice what we do with the P channel. So remember, the way we identify this thing is we look at the way the arrow is pointing. And here, if the arrow is pointing away, which means it's pointing toward the end, then the channel itself must be a P channel. Now notice the difference here. When we draw this arrow out, the circuit itself still looks the same. But up here, the VDD is a positive, right? And this is still called VDD. And over here, when we come over here and put our bias gate resistor right here, VDD would be a negative. So basically, it's like a PNP transistor. Normally, if it's an NPN transistor, we bias it with a positive power supply. And if it's a PNP transistor, we bias it with a negative power supply. Now, I didn't say always. We can actually do this a little different in that we could put our voltage, we could use a VEE voltage of a positive VEE voltage and bias a PNP transistor or vice versa. This is a P-channel JFET. Positive swing input results in an increase in drain current, and drain current becomes more positive, producing a swing in the outputs of current. So notice when we take our output across the device, when it turns on more, the output goes down, and when it turns off more, the output goes up. So what we end up with is we end up with an output signal that is 180 degrees out of phase. So an output signal that is 180 degrees out of phase. So you notice there's a lot of similarities between the common emitter and the common source. So the common emitter has basically the same features. So the common emitter, here we would have, of course here we have a high input impedance or resistance. You know, of course we've talked about this. Impedance is a term we use most often when we're talking about AC signals. And then it has a moderate output impedance. And of course, the input and the output are 180 degrees out of phase. No matter what signal you put on the input, you know, even if we put this stuff on the input, the output would be 180 degrees out of phase. This is still called a bypass capacitor. We would still bring our input, even though they show this here. Normally, since we don't have any DC bias on the input, we literally do not have to have a coupling transistor on the input, coupling capacitor on the input, which is another advantage. Now over here, this is going to be biased. So here we would have to have it's going to be sitting at a DC level, depending on what size we choose for RS. So that means on the output, we would have to have a coupling capacitor over here. So these are still called coupling capacitors. This is still called a bypass capacitor. This is in channel. It's still basically the same, but here we're going to bias it with a positive swing input. This is the same slide. This is a common gate, and it has a lot of the same characteristics of a common base amplifier. Let me choose another color so we can show that. So you can show that the input and the output current are going to be equal to each other. So here's my input coming in, and it's going to go through the channel, and then this will be my output. So this guy here has a current gain of 1. Okay, it's going to work it basically the same thing, but we're going to input on the source and output on the drain. So on a common base BJT amplifier, we input on the emitter and we output on the collector. On a common gate amplifier, we input on the source and output on the drain. So when we first started this, we didn't say they were the same, but we said they were comparable. So on a BJT and then a JFET, over here we call the control lead the base. Over here we call it the gate. Over here, our main current that we use, we refer to that as the collector. Over here, we refer to this as the drain. Over here, we refer to this as the emitter. The one that has the same basic function in a JFET is referred to as the source. But when we start looking at these amplifiers, they have basically the same characteristics. Now, one big advantage of a JFET over a bipolar transistor is we can't operate it at a higher speed because of the reverse bias junction. We can't operate it at an extremely high speed, but the biggest advantage it has is how easy we can make these things. These things are very, very, very easy to produce, and they're easy to place on a piece of semiconductor or create. We're only working with one junction and a channel. They can be very, very small. We can use them in very low power applications. They consume almost no current because we don't have to have to bias that base current on. So there's a lot of advantages to these things, and they have an extremely high input impedance. So we'll find out that these guys are used often on signals that can't provide almost no current at all, like antennas and stuff like that. So if you ever looked at the schematic of a radio, like a car radio, odds are the first transistor you're going to see is going to be an FET, and then we'll start running into bipolars, and we'll look at some of those advantages in a minute. This right here would be a common drain. Has very almost the same characteristics as a common collector. So what we do is we take our output off the source. We connect the drain directly to the power source. So here's a N channel. This is a P channel, and so and the inputs and outputs are 180 degree. Are in phase with each other. The input and output, we don't get any voltage gain off of it, but we can get a current gain. So it's basically the same features off a JFET that we get into a bipolar transistor. The preamplifiers. Now, in stereos, normally what we have is your amplifiers are set into 2 stages. We have a preamplifier, or what we affectionately refer to as a preamp. You might have heard that term before. And we're going to draw the amplifier as just a triangle. And then the preamp feeds into the power amp. And the power amp is where you get all your true power gain. When we start talking about volume controls and fading controls and balance controls, We don't try to do that on 100 watts of power. So all your controls in your stereo are in the preamp. So when you're out there in your car radio and you're setting your balance, you know, left, right balance, or your fade, your fade, the front rear fade, you know, where you can put more sound in the back than the front and all that other neat stuff. When you're setting your tone controls, all your tone controls, where you can make it, give it more bass or give it more treble or set it up for different style musics. Most of your radios now, when you start setting it up, you specify a style of music, and it automatically comes in and sets your tone controls. Well, we don't want to try to do all these controls out here where you have all these powers, so we do it inside the preamp. The actual signal that you're amplifying comes into the preamp. So in this slide, what they're doing is they're bringing the input of a microphone, and a microphone is a high impedance device. And the microphone would connect right here. So what we would do is we would match the impedance of the microphone right there. And the microphones have pretty standard input impedance. And basically, this is the only load the microphone sees, because it is not providing a gate current, because we're operating in reverse bias. And it does have a small leakage current, but you know, when we set up that circuit on Electronic Workbench the other night, we couldn't even measure that. And then we come in, and this is a common source. Common source means we take our output off the drain, and of course they draw theirs a little backwards. Here's our drain resistor. Normally we draw this schematic with this pointing up. So normally when you see a schematic, and the book just kind of draws them a little backwards. So this circuit would, we would have a C1, then we would have our drain, our gate. Then we would have our gate resistor that's got to be there, so we can set up a difference in potential between the gate and the source. And then our source resistor would be here, and then our bypass capacitor would be here, and it won't let me draw past the end. And then we would have our drain resistor up here, and then our VDD would be connected right there. This is the way it would normally be drawn on the schematic. I should have shifted it over a little bit. And then our microphone would connect right here. But what you want to do is this microphone, I don't know if you ever played with a microphone before, but they put off very, very small voltages, but almost no current at all. So what we need to do is take that very small voltage and hook it into something that's got an extremely high input impedance, so it won't load that microphone down. So this is a perfect example. Of course, this is common source. An impedance matching circuit can be stepped down, and now we understand what impedance matching is. And we know that if we can match the impedance of these devices, then we can get maximum current transfer. And this is what we're talking. So a common, and they're showing a common drain amplifier right here. And of course, we know the advantages is that it has a high input impedance or resistance, and then it has a very low output impedance. So what we're going to do, just like we do with the common collector inside a bipolar transistors, we would use a common drain to match a high impedance source to a low impedance load. And we don't get any voltage gain out of this thing. What we do is we get current gain, just like we do out of a common emitter. A voltmeter can provide high input impedance with good sensitivity by using the JFET in the front end of the circuit. So we're just getting some examples of the different ways we might use these JFETs. Voice operated relay uses the JFET as a high input matching between a microphone and a bipolar transistor. So this is what we see most often. The biggest advantage of a bipolar transistor over FETs is they can handle a lot of power. We always have a resistance in the channel. So we can make it low, but we can't get it as low as a bipolar transistor. So a bipolar transistor can handle higher voltages. They can handle a lot of power. The big advantage of FETs is that we can They have an extremely high input impedance because we're working against a reverse bias, but we're going to look here in a little while, and we can look we can look in a little while. We can see that lost my train of thought, guy. Of course, we talked about this. This is a relay up here, and we talked about the little counter EMF we get off of the relay. And you're going to have to remember this even if you take PLCs and when you start running relays with transistor output PLCs, you're going to have to put those counter EMF diodes down there. And guys, I wish I could remember what I was going to say. This would be just a volume control, it looks like. We take the output of this. This is a common, they're using this common, the output is actually coming off the source. So this would be common source. And then we come over here, we're taking output off the collector here. So this would be a common collector. So what we're doing is we don't want to get a voltage gain off the microphone. All we want to do is just get a real high input impedance. Then we get a current gain out of the FET, which now we can drive a current-based BJT. Now remember, a BJT uses a current to control a collector current, right? I'm gonna run out of room again, and then of course a FET uses a voltage, a gate voltage, to control what we call a drain current. So this would be a collector current. I just ran out of room. So this is a good example. The book gives a lot of good examples. Next thing we're going to look at, so that's your JFET. JFETs are really, really well, but we still have problems. Number one, if you accidentally forward bias the things, you could mess them up. And so what they did is they came out with some different categories. So the two categories we have of FETs, and I think we already talked about this, is we have the junction field effect. And then we have what we call a metal oxide field effect transistor, or we refer to as a MOSFET. So we refer to this as a JFET. So we have two categories of FETs. So bipolar transistors, we got two types. We got a NPN transistor and we got a PNP transistor. FETs, we're going to have a ton of those. So here we have an N channel and a P channel. What do you think we have on our model, your MOSFETs? Well, we have N channels and we have P channels. And we have two categories of this. We have what we call D MOSFETs, which we'll look at in a minute, which has a P channel and an N channel. I don't have any room in a P channel. And then we have what we call E MOSFETs, which has an N channel and a P channel. So you look at MOSFETs, we got one, two, we got 1, 2, 3. We got two types. So we got three different types, right? Because these are all metal oxide. So we got JFETs, we got D MOSFETs, and we got E MOSFETs. Every one of them's got their own characteristics. They are not the same. If they were the same, we wouldn't have three different types. Each one of them has got a P channel, and an N channel. So we got a P channel and an N channel JFET. We got a P channel and an N channel D MOSFET, and we got a P channel and an N channel E MOSFET. And we'll see which one the book covers first. Looks like they're covering the. This is a D MOSFET right here. And notice we have 3 leads. These guys will come with either 3 leads or they'll come with 4 leads. So what we do when we make a MOSFET is they start off with what we refer to as a substrate. And a substrate is just a base that we build with a MOS transistor in. And then what we do is we come in and we create a channel similar to that. And then what we'll do is we'll come over here. Let me do the channel because we've got to be able to separate it. Then what they do, and how it got the name MOSFET, is that they actually grow silicon rust, silicon oxide. They grow a layer of silicon rust on top of this. So and rust is often referred to as oxide. So with metal rust, we refer to that as oxide. Then what they do is they come up here and the gate lead is actually isolated from the channel. So MOSFETs have no p-n junction, absolutely no p-n junction. So what we'll do is they put the strip of metal up here, and then we come up here and we connect a lead to it. So we come over here and connect these two leads. We change back to white. Okay. So one of these leads right here would be the drain. This would be the source. And then this right here would be the gate. And there is absolutely no p-n junction in a MOSFET. You have no p-n junction. Now sometimes to establish a reference is they'll put a lead out here. Now 90% of the time they'll take the lead and to separate a source, they will connect it to the source. And there's no current flow between the source and the substrate because there's no difference in potential. So we're going to get these things either with 4 leads, or we'll have a substrate lead, which is 90% of the time. I've never seen one connected anywhere else, so it always amazes me why they do that. We have a substrate, if you can read this, and we have a drain, and then we have a source, and then we have a gate. Now this is the symbol. So notice on this symbol, and this is an N channel because the gate, we've got our arrow pointing toward the channel, so this is an N channel. But notice they actually show the gate isolated from the channel, and that's that oxide. That's that oxide layer that we have. So there is absolutely no p-n junction in a MOSFET transistor. Okay. Now sometimes what they'll do is they'll take the substrate, since it's so commonly done, they'll take the substrate and connect it to the source internal. So these MOSFETs will have 3 leads. They would be a 3-lead MOSFET, and then this would be a 4-lead MOSFET. I don't know if the book talks about this or not, but it should. Like I said, I didn't bring my book for some reason, so I'm teaching this off of just knowledge that I know. We have this oxide layer is extremely thin, and so what we're doing is we're basically forming a little capacitor right here. And so we can transfer and if you remember, capacitors operate off an electrostatic field. So basically, if you can visualize the channel as being one plate and this as being another plate, then these two things can interact with each other without ever even touching. But what happens if we ever puncture a hole through this oxide layer, which is extremely small or thin, then we've damaged our FET. So one thing you got to be really watch out with these MOSFET is they're very susceptible to damage by static discharge. So these guys right here, you need to keep them in static foam. A lot of times when you buy an FET, it'll have a little wire spring wrapped around the leads to keep the leads from ever getting at a difference in potential. And this causes a problem because sometimes people forget to take that spring off there. So what you're supposed to do is when you solder them into your circuit card, you're supposed to solder them in and everything so you can handle them. And then the last thing you're supposed to do is grab this little ring and pull off that little spring clip. And so it's got a little ring that sticks out from it. And I don't think we have any moss. So they have a ring that goes around it, and it wraps around, and it'll have a little ring coming out here. So you can come up here and grab this with a pair of needle nose pliers and pull them off. But you need to wait to do that until you get mounted and soldered into the circuit card, and that way it can dissipate the electrostatic charge to the card. But you got to remember to pull off that little spring before you throw power on the thing. So this is showing you how they make it. This is the first one we're going to look at. Now notice on this one, which is not what they showed on the previous slide, this would be an N channel, and the substrate is P. So what we do to make an FET is whatever the channel is, the substrate would be the actual opposite charge. So here's the insulating material. It's nothing but silicon oxide, which is a very good insulator. Then the substrate material is just what we mount the channel into. Then we have our base. Now what we have here is we don't have a channel. We do not have a channel. So an enhancement mode MOSFET or eMOSFET has no channel until you create one. And how do you think you create one? Well, you create one by putting a DC charge on the gate. So what I would do is I would come over, this is an N channel. So what I would do is I would come over here and put a P on here. Now this is going to be opposite of a JFET. A JFET is reverse bias. Well, we're not really reverse biasing here. So on an N channel JFET, 0 volts, you get maximum current flow. So you put a minus voltage on the gate, and we call that depletion mode. We call that a depletion mode. So the voltage you put on the gate makes the gate smaller, makes the channel smaller on a JFET. But what we're doing here on this MOSFET is we're going to put a P on the gate, which is what it's going to do. Well, a P has a positive charge. So this guy right here, I have a big positive charge. And what does an N have? It has a negative charge. So what it's going to do is it's going to cause these electrons to migrate in the channel. As soon as I hit what we refer to as a threshold voltage, then we have a channel. Now we're not forward biasing this thing, but if it was a JFET, this would be forward biasing by putting a P on the P and an N on an N, right? You understand that? So we're not really calling this forward bias, but when we do this, what we do is we create this channel. And as soon as we create that channel, as soon as you exceed the threshold voltage of the eMOSFET, then you have current flow to it. And that's what they're showing us here. Okay. So what happens is we create a channel. With a positive, we create a channel. But you have to exceed the threshold voltage. These guys are used a lot as switches because they have almost infinite impedance when they're turned off because there is no channel between the drain and source or resistance. And when we turn these things on, they saturate and we create that channel. So these guys right here are used a lot as switches. MOSFET transistors. eMOSFET. eMOSFET means we put a voltage on there that makes the channel bigger. And since we have no channel at all, this is called an enhancement mode MOSFET. But if you look it up in a parts book thing, they're going to call this an eMOSFET. Used predominantly as a switch, a very high-speed switch. Has extremely high resistance when it's turned off between the drain and source, and has very low resistance when we turn these puppies on. So we use these as switches all the time. These are the predominant guys used inside digital circuits, in microprocessors, and in variable speed drives, or variable frequency drives, which we'll look at later. So this is the symbol of an eMOSFET. And they don't show the substrate. It could have another lead. So this guy here could have 3 leads. If it only shows 2, 3, could have 4 leads. But here they show the substrate being connected to the source. Okay. But notice they draw it with the channel broke. So the channel is not made. So when we did the symbol for our JFETs, we drew the channel made. here when they draw the symbol for the E-MOSFET, they draw the channel broken. So the only way we're going to create that channel is if we come over here and put a positive on the gate, and then we pull it. So here's the channel. So notice the channel is broken. We put a positive on the gate if it is we put a negative on the gate if it's a P channel. We would put a positive on the gate if it's an N channel. Okay, I didn't notice these were different. And then once we do that, we create a channel. Once you get up to a threshold voltage. Once you exceed the threshold voltage, this guy cuts on. Once you drop below that threshold voltage, this guy cuts off. Very, very, very popular, used in digital circuits. Very popular. Depletion mode, we'll look at this in a minute. What we're going to do, this is 40 minutes on this lecture, so we're going to stop. So that's the enhancement mode MOSFET. Enhancement mode means you put a potential on the gate that causes the channel to get bigger. Depletion mode means you put a potential on the gate that makes the channel get smaller. All JFETs operate in the depletion mode. We have a type of MOSFET that only operates in the enhancement mode, which means we put a polarity. So if it's an N channel, we put a positive on the gate. If it's a P channel, we would put a negative on the gate. And that would enhance the channel. And once we get up to the threshold voltage rating of the MOSFET, then that thing cuts on. When we get below the threshold, it cuts off. The input impedance approaches infinity, extremely high. It would be about the impedance or resistance of a capacitor, which we can't even measure, right? You understand that. The output impedance when it saturates, would be very, very low, and which is what we're looking for in a digital switch. So all your microprocessors are made out of MOSFETs, so you got to be careful. As soon as we said MOSFET, what you got to understand is these guys are susceptible to damage by static electricity. So you're going to have to. So what I'm going to show you is I'm going to show you some of the things we have to take in consideration when we deal with MOS circuits. You got to be a little careful with them. You can't handle them directly out of the pack. You got to be careful, make sure you're discharged, or make sure you and the MOS circuits are at the same potential. So what I'll do when we come back after Thanksgiving, I'll make a point to, and if I don't, remind me to show y'all some of our static mats and some of our wristbands and stuff that we use when we handle MOS circuitry. If you're going to work with memory inside a computer, all your memory is made out of MOS transistors, which means these guys are very susceptible to damage by static discharge. And and a lot of times you have a static discharge, people, and you do not even know it. So, but just taking very few safety precautions, and it's not safety because you're going to hurt you. It's safety because you're going to hurt your device that you have out there. Very few safety precautions. You can work with these things for years and years and not have any problems at all. So I'll show y'all that. We'll go into the DMOSFET, and then we'll come back and we'll come back and we'll tie all this up. But I'll go ahead and post this and put it online. I think this is going to work out better instead of me trying to give y'all a 3-hour lecture that you have to watch one time, to go ahead and spread it out into smaller 40, 30-minute lectures for you. So hope y'all have a blessed night, and I'll post another one, the last one tomorrow night, and this should finish our lectures on MOSFETs. Try to open up a question and answer period for you where you can submit your answers. You can always submit your answers if you're texting with me. You can always submit your answers, your questions through email. Or, if you're sitting there with your phone and you see a question pop up and you want to go ahead and answer it, ask that question, you can go ahead and do that. Or you can always go ahead and make sure you write your questions down. And what we'll do when we come back, I think on the 28th, is we'll start off with a nice question and answer period to see if y'all got any questions about these FETs. I think there is one lab in the lab book that we use on FETs. I think it's an N-channel JFET. It's a very simple lab. I can't remember which number it is, but it's not. We're not going to do a lot of amplifiers with FETs. We're not going to do very much. I think, like I said, I think there's only one lab in the book. So y'all have a blessed day. Hope y'all have a great Thanksgiving. And like I said, I post the last lecture tomorrow. I don't know when I'll get this up. It'll take a while for me to send it up to UTEP. All right, signing off.